There is a moon orbiting Saturn that looks like something tried to crack it open. Tethys is small, frozen, and made almost entirely of water ice. It should be unremarkable, but running across its surface is a canyon system so enormous that it stretches nearly 3/4 of the way around the entire world. Ithaca Chasma is roughly 2,000 kilometers long, 100 kilometers wide, and up to 5 kilometers deep, carved into a body barely 1,000 kilometers across. The scar is so large relative to the moon that when Voyager first photographed it, scientists struggled to explain how a feature that immense could exist on a body that small. What ancient event or internal transformation could wound an entire moon on that scale? Tonight, we find out. If you enjoy the kind of deep science that takes you to places most people never hear about, a like and a subscribe go a long way toward helping us keep making these. We appreciate every single one of you that supports the channel. Also, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, are you comfortable? Okay, let's begin. Picture Saturn. Not the textbook version, not the tidy diagram with labeled rings and numbered moons. Picture it the way spacecraft have seen it, after crossing billions of kilometers of empty space to reach a planet so immense that more than 700 Earths could fit inside its volume. The rings stretch outward in every direction, impossibly thin relative to their width. A disk of ice and rock particles that catches sunlight and scatters it in ways no single photograph has ever fully captured. Around the planet, more than 100 known moons trace their own paths through the gravitational architecture of the system. Some are enormous. Titan, the largest, exceeds the planet Mercury in diameter and hides beneath a thick orange atmosphere, dense enough to support weather systems and methane rain. Others are tiny, irregular fragments of captured debris, barely a few kilometers across. Dark and misshapen, drifting at the far edges of Saturn's influence. And somewhere in the middle of the family, orbiting closer to the rings than most people realize, there is a moon that looks, at first glance, like nothing worth stopping for. Tethys is white, brilliant, almost blindingly white, reflecting more visible light than nearly any other solid body in the solar system. Its geometric albedo exceeds 1.2, meaning it scatters back more light than a perfectly diffuse white surface would. From a distance, it resembles a ball of clean snow drifting through the dark. A small, featureless sphere with no obvious color variation, no visible activity, no drama of any kind. It does not glow with volcanic fire like Jupiter's moon, Io. It does not spray plumes of water vapor into space like its inner neighbor, Enceladus. It does not hide beneath a veil of atmospheric haze like Titan. Tethys simply exists, frozen, quiet, and still, presenting the same hemisphere towards Saturn at all times as it completes one orbit every 45.3 hours, gravitationally locked in phase with the planet it circles. It has no atmosphere, no weather, no seasons in any meaningful sense. The surface temperature hovers around 86 Kelvin, roughly minus 187 degrees Celsius, a cold so deep that the water ice composing the surface behaves not like the fragile, slippery material you know from everyday life, but like stone. Part of the reason Tethys is so extraordinarily bright is that it orbits within Saturn's E-ring, a broad and diffuse ring of microscopic ice particles that most people have never heard of because it is far too faint to see from Earth. Those particles originate from the geysers of Enceladus, which erupt water ice into space at high velocity. Some of that material spreads outward through the Saturnian system, and Tethys, orbiting at a distance of roughly 295,000 kilometers from Saturn's center, sweeps through this faint haze of ice grains on every orbit. Over time, the grains coat the leading hemisphere in a continuous dusting of fresh, bright material, enhancing the moon's already remarkable reflectivity. The trailing hemisphere, by contrast, is bombarded by high-energy electrons and ions from Saturn's magnetosphere. These charged particles slam into the ice surface at enormous speeds, breaking molecular bonds and chemically altering the topmost layer. The result is a subtle yellowish tint, visible only in enhanced color imaging, a faint stain created not by geology but by radiation. Up close, the surface reveals its true age. Every part of Tethys that Cassini's cameras have imaged at high resolution is covered in impact craters. They range from tiny pits a few hundred meters across to basins tens of kilometers wide. They overlap, cross-cut, and crowd against one another so densely that in many regions there is no unscathed surface left. On a world with no atmosphere to erode them, no wind to fill them with sediment, no rain to smooth their rims, and no volcanism to resurface the terrain, every impact that ever struck Tethys left a permanent mark. The surface is a cumulative record of bombardment stretching back billions of years, an archive of collisions written in ice and frozen in place. Nothing fades, nothing heals, the craters simply accumulate. None of that by itself is unusual for a small icy moon. What made scientists stop and look twice at Tethys was not the cratering, it was what lay beneath it. Running across the face of the moon, stretching from the northern latitudes down through the equator and deep into the southern hemisphere, is a canyon system so enormous that describing it accurately sounds like exaggeration. Ithaca Chasma is approximately 2,000 kilometers long. That distance represents nearly 3/4 of the moon's entire circumference. The canyon averages roughly 100 kilometers in width. In places, it plunges 3 to 5 kilometers deep into the icy crust. Those numbers are large in absolute terms. They become almost absurd when you measure them against the body they are carved into. Tethys has a mean diameter of only about 1,062 kilometers. The canyon stretches a distance nearly twice the moon's own width, wrapped around the surface like a line drawn across a globe with a blade far too large for the world it cut. To feel the mismatch between feature and body, consider this. If you could shrink Tethys to the size of a basketball, Ithaca Chasma would be a groove carved from one side nearly all the way around to the other, wide enough to catch your fingertip and deep enough to feel distinctly against the smooth curve of the ball. On a basketball, that groove would be immediately obviously wrong. It would look like structural damage. It would look like something tried to split the ball along a seam and very nearly succeeded. That is what Ithaca Chasma looks like on Tethys. Not a subtle surface crack, not a wrinkle in the terrain, a wound so large that it reshapes your perception of the entire body the moment you see it. This is not a fissure in the ordinary sense. This is not a trench you could peer across or a ravine you might hike through in an afternoon. This is a geological structure that dominates the moon at every scale. If you stood on one rim and looked toward the other, the far wall would be beyond the visible horizon, hidden by the curvature of a world so small that the horizon closes in at barely 1.5 kilometers for a person standing on the surface. If you followed the canyon from end to end, you would walk a distance comparable to the span of the continental United States, and you would be walking in a surface gravity roughly 1/60th of Earth's. on ground composed of water ice so cold that it responds to stress the way granite does. Behind you and ahead of you, the walls of the canyon would rise like frozen cliffs of pale ice, terraced in places, sheer in others, extending in both directions until the curvature of the moon carried them gently out of sight. Overhead, nothing. No sky, no atmosphere, no sound. Just the black of space and the faint glow of Saturn hanging in the distance, enormous and striped, filling a portion of the sky that would make any planet you have ever seen from Earth look insignificant. The question that defines every scientific discussion of Tethys begins here, at the edge of this scar. How did it get there? How does a moon this small, this cold, and this geologically quiet end up carrying a fracture system this immense? And what does it tell us that the canyon is not even the only enormous wound on the surface? Before those questions can be answered, it helps to understand what Tethys is built from, because the moon's composition is itself part of the puzzle, and it makes the canyon stranger rather than easier to explain. Tethys has a mean density of approximately 0.984 grams per cubic centimeter. In everyday terms, that number seems unremarkable, sitting just below the density of liquid water. In planetary science, it carries extraordinary diagnostic weight. The density of a body reveals what it is made of. Earth's moon, composed of silicate rock and a small iron core, has a density around 3.34 grams per cubic centimeter. A moon made of a roughly equal blend of rock and ice falls somewhere near 1.5 to 2. A moon whose density is essentially identical to pure water ice, barely below 1, is telling you something unambiguous. There's almost no rock inside it. Tethys is composed overwhelmingly of water ice with only a tiny fraction of silicate material mixed in, making it the least dense of all the major moons in the solar system. Spectroscopic observations of the surface confirm this from the outside. The infrared signature is dominated by water ice absorption features. No significant amounts of silicate minerals, metals, or complex organic compounds have been detected. The small quantity of dark material visible in certain regions appears to consist of minor impurities delivered by meteoritic bombardment or produced through chemical alteration by energetic particles from Saturn's magnetosphere. This near-total ice composition matters for the canyon question in two distinct ways. First, it determines how the interior responds to stress. Rock fractures when stressed beyond its yield point, and ice does the same. But ice possesses an additional property that rock does not share. When liquid water freezes into solid ice, it expands, a property nearly unique among common substances, and one whose consequences become enormous at planetary scale. If Tethys ever possessed a subsurface ocean of liquid water, and if that ocean eventually froze, while the outer shell was already locked rigid, the expanding ice would have pressed outward against the crust from every direction. The shell would have had no way to accommodate the growing volume beneath it. Something would have had to give. The mechanics of how that works, and why the expansion of freezing water can crack an entire world, will become central to this story. For now, the point is that Tethys's nearly pure ice composition does not just make the canyon harder to explain. It makes the canyon possible in the first place, through a mechanism that depends on a molecular property no rocky world possesses. Second, the near absence of rock means a near absence of radioactive elements. On rocky worlds and rock-bearing moons, the slow decay of long-lived isotopes of uranium, thorium, and potassium generates heat, that sustains geological activity over billions of years. Earth's own interior is still partially molten in large part because of radiogenic heating. A body made of almost pure ice has virtually none of this internal fuel. Standard thermal models of a moon with Tethys's composition predict that it should have cooled rapidly after formation and frozen solid relatively early in its history, becoming a geologically dead world within the first billion years or so. The fact that something clearly happened to the surface on an enormous scale, something that required significant internal heat, is the first indication that the simple story of a quiet frozen ice moon is missing a critical chapter. Tethys occupies a specific and notable position within Saturn's family of moons. It is the fifth largest of the major satellites, smaller than Titan, Rhea, Iapetus, and Dione, but larger than Enceladus and Mimas. Its orbit is nearly perfectly circular, with an eccentricity so close to zero that the difference between its closest and farthest approach to Saturn is negligible. It is locked in an inclination resonance with the smaller inner moon, Mimas, meaning the two bodies exchange subtle gravitational nudges that maintain a fixed ratio between their orbital tilts. Crucially, this resonance does not currently force any meaningful eccentricity into Tethys's orbit, and does not generate significant tidal heating. Whatever warmed the interior in the past is not operating today. The present-day Tethys is gravitationally calm, tracing a stable circular path through a region of the Saturn system that shows no sign of dynamical disruption. Two small companion moons share that path. Telesto and Calypso occupy the stable Lagrangian points in Tethys's orbit, one leading by 60 degrees and the other trailing by 60 degrees. These tiny bodies, each only a few tens of kilometers across and irregularly shaped, have been gravitationally trapped in these positions for what is likely millions of years. Their stability tells scientists something important about the orbital environment. It has been undisturbed for a very long time. Tethys is not currently being tugged, jostled, or perturbed by anything dramatic. It drifts along its circular path carrying its small companions with it, presenting a picture of orbital serenity that stands in stark contrast to the violence written across its surface. The discovery of what that surface actually looks like is a story that spans 3 centuries of observation and 3 distinct eras of space exploration. Giovanni Domenico Cassini first observed Tethys on March 21st, 1684, from the grounds of the Paris Observatory. He was an Italian-born mathematician and astronomer who had been recruited to France by King Louis XIV to serve as director of the observatory, and he used a large aerial telescope to study Saturn's system. Aerial telescopes of that era suspended the objective lens on a tall mast or pole, with the eyepiece held separately by the observer at a considerable distance. The arrangement was ungainly and fragile, but it reduced the chromatic aberrations that plagued shorter refracting instruments. Through this method, Cassini identified 4 of Saturn's moons: Iapetus, Rhea, Dione, and Tethys. He named them collectively the Stars of Louis, in honor of his royal patron. The individual mythological names came later, proposed by the English astronomer John Herschel, who suggested that Saturn's moons should bear the names of the Titans from Greek mythology, the generation of gods associated with Kronos, the Greek equivalent of the Roman deity Saturn. Tethys was a Titaness, a daughter of Uranus and Gaia, and a goddess of the fresh water that fed the world's rivers. For nearly 300 years after that first sighting, Tethys remained a point of light. Astronomers refined their knowledge of its orbit, its period, and its rough size, but the surface was invisible to every telescope on Earth. There was no way to guess what features it carried, what its terrain looked like, or whether it held anything that would distinguish it from any other small frozen body drifting through the outer solar system. The space age opened the first window, though the view was narrow. Pioneer 11 flew past Saturn on September 1st, 1979, the first spacecraft ever to reach the ringed planet. It carried imaging instruments, but its trajectory brought it no closer than roughly 354,000 kilometers from Tethys, and the resulting pictures were too low in resolution to show any surface detail. The moon appeared as a small, bright, smooth disk. Scientists could confirm its high reflectivity, but little else. At that point, the best information anyone had about Tethys' surface was that it reflected a great deal of sunlight, which was consistent with a composition of clean water ice, but told them nothing about what that ice looked like up close. The real revelation arrived with the Voyager missions. Voyager 1 reached Saturn in November of 1980, passing within roughly 415,000 kilometers of Tethys. Its cameras, far more capable than Pioneer 11's, captured the first images showing actual surface features. Even through the grainy resolution of early 1980s imaging technology, one structure was immediately startlingly obvious. A long, dark line cut across the visible face of the moon, running roughly from north to south, extending so far that it disappeared beyond the limb in both directions. That line was Ithaca Chasma. Its scale was apparent even in the limited data. This was not a hairline fracture. This was not a subtle groove. Something had carved a trench across a substantial fraction of the moon's visible surface, and no one had predicted anything like it. Voyager 2 arrived in August of 1981 and passed significantly closer, within approximately 93,000 kilometers. Its cameras delivered sharper images that revealed both Ithaca Chasma in greater structural detail and the massive Odysseus crater on the opposing hemisphere. The pictures showed the canyon's steep, shadow-casting walls dropping into darkness below. They showed the Odysseus basin's flattened floor spreading across a circular area that consumed nearly 2/5 of the visible disk. And they showed the dense, ancient cratering that covered every exposed surface between the two giant features, a carpet of overlapping scars that spoke to billions of years of uninterrupted bombardment. Scientists studying the Voyager data recognized that they were looking at a small world carrying two features, each individually extraordinary relative to the moon's size, each raising fundamental questions that the data in hand could not resolve. The Voyager encounters established the foundation of what was known. Ithaca Chasma ran roughly north to south across more than 1,000 kilometers of visible surface, with a width averaging around 100 kilometers and depths reaching several kilometers into the crust. Odysseus crater measured approximately 450 kilometers in diameter, spanning nearly 2/5 of the moon's full width. On a body as small as Tethys, an impact of that magnitude should have been catastrophic. The energy required to excavate a crater that large relative to the size of the target body approaches the energy needed to destroy the body entirely. The fact that Tethys survived told scientists something critical about the state of the moon at the time of impact. A fully frozen, rigid ice body of that size would have shattered. Tethys endured because its interior was warm enough to absorb and distribute the energy, deforming plastically rather than fracturing catastrophically. The moon had to be at least partially molten when the blow landed. But Voyager was a flyby mission. The spacecraft gathered data during a brief window of approach, snapped its pictures, made its measurements, and kept going. It could not return for a second look. It could not observe the same features under different lighting angles to reveal topographic detail. It could not produce three-dimensional terrain maps, and it could not count craters on the canyon walls with enough precision to establish when the feature formed. The questions Voyager raised would have to wait more than 2 decades for an instrument capable of answering them. That instrument arrived at Saturn on June 30th, 2004. The Cassini spacecraft, named after the same astronomer who first spotted Tethys more than 3 centuries earlier, entered orbit around Saturn after a journey of nearly 7 years from Earth. Unlike the Voyager probes, which gathered their data in passing and continued outward into deep space, Cassini stayed. For over 13 years, it circled Saturn in a complex series of orbits, making repeated close approaches to the planet's moons, including multiple dedicated flybys of Tethys. It carried a narrow-angle camera that could resolve features on icy surfaces at scales of hundreds of meters per pixel. It carried a visual and infrared mapping spectrometer that could identify the chemical composition of surface materials remotely, and its overlapping image sequences, captured from different vantage points during successive orbits, allowed researchers to construct stereo-derived topographic maps that revealed the three-dimensional shape of surface features with a precision the Voyager era could never have approached. What Cassini showed at Tethys transformed the scientific understanding of the moon. Ithaca Chasma was not a simple crack or a single clean-walled trench. It was a complex graben system, a class of geological feature formed when a block of crust drops downward between 2 roughly parallel faults, driven by extensional forces pulling the surface apart. The walls were terraced, stepping down from the surrounding plains in multiple, discrete levels, rather than falling as a single precipitous cliff. Subsidiary fractures branched outward from the main channel, spreading across the adjacent terrain like cracks, radiating from a central break in a pane of glass. And along the flanks of the canyon, the surface was slightly but measurably elevated, rising above the average terrain in a pattern known as flexural uplift. The bending response of a rigid plate when it is broken, and one side subsides under its own weight. The canyon was not a superficial surface scar. It was a structural feature that had reshaped the ice shell to a depth of kilometers and produced visible deformation across a zone far wider than the canyon floor itself. These details mattered enormously because each one constrained the physics of the event that created it. By modeling the canyon's topographic profile as a broken elastic plate, researchers calculated the effective elastic thickness of Tethys's ice lithosphere at the time the fracture formed. The answer was roughly 5 to 7 kilometers. From that thickness, combined with what is known about how ice deforms under stress at different temperatures, they derived the heat flux flowing through the crust when Ithaca Chasma opened. Approximately 18 to 30 milliwatts per square meter. Those numbers became one of the most important constraints in the entire Tethys story. Thermal models of a moon with Tethys's composition, nearly pure ice containing almost no radioactive elements to generate internal warmth, predicted heat fluxes at least 4 times lower than what the canyon's structure required. Ithaca Chasma was telling scientists, through the language of its own geology, that Tethys was significantly warmer at the time of the canyon's formation than its composition alone should have allowed. Something was generating heat inside the moon that the standard models could not account for. And whatever it was powerful enough to soften the interior, thin the lithosphere to a shell only a few kilometers thick, and ultimately crack the crust on a global scale. Cassini also brought Odysseus crater into sharp focus. At roughly 450 kilometers in diameter, Odysseus is one of the largest, well-preserved multi-ring impact basins on any icy body in the solar system. Its outer ring is defined by steep, cliff-like walls that descend to broad internal terraces. A prominent inner ring of mountainous massifs forms a crown-shaped band roughly 140 kilometers across. The central complex includes a pit 2 to 4 kilometers deep, surrounded by peaks rising 6 to 9 kilometers above the crater floor. The structure preserves the anatomy of an enormous impact event. The rebound signatures of shock waves that penetrated deep into the moon at the moment of collision. But the most revealing characteristic of Odysseus is what time has done to it. A fresh impact crater of this magnitude would feature razor-sharp rim crests, precipitous inner walls, and a towering central peak. Odysseus has none of these in their original sharpness. The floor has sagged, gradually relaxing downward until it conforms approximately to the spherical curvature of the moon's surface. The rim has slumped. The central peak has partially collapsed. The entire basin appears softened, as though the surrounding ice flowed slowly under gravitational stress over immense spans of time, seeking a lower energy configuration. This process is called viscous relaxation. Even at Tethys's extreme surface temperatures, ice is not a perfectly rigid material across timescales of billions of years. Under sustained load, it creeps, deforming grain by grain at rates far too slow to observe directly, but producing cumulative effects that reshape large structures over geological time. The softened profile of Odysseus told scientists that the crater formed on a world whose interior was warm enough, at least in the period following the impact, for this slow, viscous flow to operate with meaningful efficiency. The spatial relationship between the two features is what originally made scientists suspect they were connected. Ithaca Chasma lies roughly along a great circle that passes near the point on Tethys directly opposite Odysseus crater. In impact physics, antipodal focusing is a well-documented phenomenon. When a large body strikes a sphere, seismic energy radiates outward in all directions through the interior. The wavefronts wrap around the body and converge on the far side, focusing their energy at the antipodal point. In sufficiently violent impacts, this focused energy can produce fracturing, disrupted terrain, or volcanic activity on the opposite hemisphere. Mercury provides one of the clearest examples. The Caloris Basin, one of the largest impact structures in the inner solar system, has a region of chaotic and hilly terrain at its exact antipode that is widely interpreted as a product of focused seismic energy from the impact. The hypothesis that Odysseus created Ithaca Chasma through this mechanism was elegant. The geometry supported it. The physics was plausible. The shock wave from an impact powerful enough to excavate a 450-kilometer basin would have carried devastating energy through the interior, and a circumcircular fracture on the far side, analogous to an outer ring graben in a multi-ring basin, was a credible, predicted outcome. For years, the idea stood as the leading explanation for the canyon's existence, tidy and convincing. And then Cassini's high-resolution images allowed scientists to count the craters on both features with real precision, and the crater counts told a different story entirely. What those counts revealed, and why they forced the entire scientific conversation to pivot toward a much harder and more uncertain explanation, is where the story takes its sharpest turn. Because the timeline written in those ancient pockmarks pointed to a canyon that was already old when the Odysseus impactor arrived. And if the fracture existed before the crater, then the impact could not have caused it. And the true origin of Tethys' enormous wound was something deeper, something internal, something that demanded a source of energy this tiny ice world should never have possessed. The method sounds deceptively simple. You photograph a surface, you count the craters. The older a terrain is, the more craters it has accumulated. Because impacts continue to strike at a roughly predictable rate over geological time. A heavily cratered region has been sitting undisturbed for longer than a lightly cratered region. By comparing the crater density on two different areas of the same body, you can determine which area is older, even without knowing the absolute ages in years. This is called crater counting chronology, and it is one of the most powerful tools planetary scientists possess for reading the history of a world that has no fossils, no sedimentary layers, and no other conventional record of time. The technique was refined on the Moon, where the returned samples from the Apollo missions allowed researchers to link specific crater densities to specific absolute ages. That calibration, sometimes called the lunar chronology, can be extended to other bodies in the solar system by adjusting for differences in impact rates, impactor populations, and surface gravity. The process involves uncertainties, particularly when applied to the moons of the outer solar system, where the impactor population is different from the one that shaped the inner planets, but the relative ages it produces, which surfaces older than which, are robust. When researchers at the German Aerospace Center applied this technique to Cassini's high-resolution images of Tethys, the results overturned the prevailing explanation for the Moon's most famous feature. The analysis focused on two areas. The first was the terrain along and within Ithaca Chasma itself. The second was the floor and surrounding area of Odysseus crater. If the canyon had been caused by the Odysseus impact, the two features should share the same age, or the crater should be marginally older, since it would have been created by the same event or slightly before the stress fractures propagated outward. Instead, the crater density on the terrain surrounding Ithaca Chasma was measurably higher than the crater density within Odysseus. Using the lunar-like chronology model, the team estimated that Ithaca Chasma formed approximately 4 billion years ago, placing it in the earliest era of the solar system's history. Odysseus, based on the lower crater density on its floor and inner walls, appeared younger. The implication was stark. The canyon already existed when the impactor that created Odysseus arrived. The fracture system was carved into the surface first. The giant crater came later, punching into a world whose crust had already been split open by an entirely different process. The elegant explanation that had satisfied scientists for years, the idea that a single catastrophic impact sent a shockwave through the Moon and cracked the far side open, could not survive this timeline. The cause had to precede the effect, and the crater count said it did not. This finding, published by Gysi and colleagues in 2007, did not erase Odysseus from the Tethys story. An impact of that magnitude still reshaped the Moon. The shockwave still propagated through the interior. And some researchers have noted that the Odysseus event may have reactivated or modified pre-existing fractures in the crust, even if it did not originally create them. A study noted in 2016 suggested that while the canyon itself was not produced by the Odysseus impact, the event may have been responsible for certain bands of large ice particles observed stretching across Tethys's northern and southern hemispheres. Features that could represent secondary effects of the seismic energy released during the collision. The impact mattered, but it was not the origin. Once the impact hypothesis was weakened, the scientific conversation had to change direction entirely. If the canyon was not formed by an external blow, then the force that created it came from within. And to understand what internal process could crack the crust of an entire moon on a global scale, scientists had to reconstruct what Tethys looked like on the inside, billions of years ago, during an era for which the only surviving evidence is the shape of the surface itself. Start with what the density tells us. At 0.984 grams per cubic centimeter, Tethys is essentially a ball of water ice. The small fraction of silicate rock mixed in is so minor that models of the moon's interior typically treat it as a homogeneous ice body, not a differentiated world with a rocky core and an icy mantle the way some larger moons are structured. Whether Tethys ever differentiated at all, whether whatever rock it contained ever sank to the center, remains an open question. Some researchers believe the moon's nearly uniform density argues against significant differentiation. Others note that with so little rock present, differentiating or not differentiating would produce only a minor difference in the bulk density, making the question difficult to resolve with current data. What is less ambiguous is that Tethys once contained liquid water in its interior. The evidence is indirect but compelling. The formation of Ithaca Chasma itself provides the strongest argument. The canyon's dimensions, its structural characteristics as an extensional graben, and the heat fluxes required to produce a lithosphere thin enough to fracture in the observed pattern, all point to a moon that possessed a warm, partially liquid interior when the fracture formed. The freeze expansion mechanism in which an internal ocean solidifies and expands, cracking the rigid outer shell from below, remains the most physically straightforward explanation for how a body made of water ice could produce a global scale rift. But the heat flux question lingers. The values derived from the canyon's topographic profile, 18 to 30 milliwatts per square meter, were already several times higher than what standard thermal models of a nearly rock-free ice moon predicted. Then, subsequent research pushed the constraints further. In 2017, White and colleagues used the relaxation state of craters across Tethys' surface to estimate past heat fluxes independently. Crater relaxation works as a geological thermometer, but understanding why requires a brief detour into how ice behaves under stress at different temperatures. At the temperatures currently prevailing on Tethys' surface, roughly 86 Kelvin, water ice is brittle. It responds to stress the way rock does on Earth. Apply force to it and it resists, then breaks. A crater that forms in ice at this temperature holds its shape almost indefinitely, because the material is too rigid to flow. But as the temperature rises, even modestly, ice begins to cross a critical boundary. Somewhere between 100 and 160 Kelvin, depending on the strain rate and the grain size, water ice transitions from brittle to ductile behavior. It stops breaking under stress and starts flowing. Not flowing like a river, but creeping, deforming grain by grain under the sustained pull of gravity at rates that are immeasurably slow in human terms, but geologically transformative over millions of years. This brittle to ductile transition is what makes crater shapes so diagnostic. When a crater forms on an icy surface, gravity immediately begins working to flatten it. The raised rim wants to subside. The deep floor wants to rise. If the ice is cold enough to remain brittle, gravity cannot accomplish this because the material is too strong to yield. The crater retains its fresh shape essentially forever. But if the ice beneath the surface is warm enough to enter the ductile regime, the crater begins to relax. The rim sags. The walls slump inward. The floor slowly rebounds upward. Over tens to hundreds of millions of years, the crater loses its topographic definition, smoothing toward the surrounding terrain like a footprint in warm clay slowly losing its edges. The rate at which this happens depends directly on the temperature, and therefore on the heat flux flowing through the crust from below. A higher heat flux pushes the brittle ductile transition closer to the surface, allowing relaxation to operate more efficiently and at shallower depths. By measuring how much a crater has relaxed from its original sharp profile and modeling that relaxation at different heat fluxes, researchers can extract a quantitative estimate of how warm the ice was during the period when the relaxation occurred. White's analysis found that several craters on Tethys had experienced heat fluxes reaching up to 60 milliwatts per square meter. That number is remarkably high for a body of this composition. It suggested not just a warm interior at the time of Ithaca Chasma's formation, but sustained or repeated episodes of elevated heat flow across different regions and possibly different time periods. The surface was recording thermal conditions far more intense than a passively cooling ice moon should have ever experienced. A 2023 study in the Planetary Science Journal carried this analysis further by examining how heat fluxes varied across both space and time on Tethys. The researchers found that different regions of the surface preserved evidence of different thermal histories, with the area around Ithaca Chasma and the nearby Telemus Basin showing particularly high past heat flows. The thermal story was not uniform. Some parts of the moon had been hotter than others, and the heating may not have been a single event, but a sequence of episodes stretched across a significant fraction of the moon's history. This layered thermal record transforms the picture of ancient Tethys from a simple freeze and crack event into something more complex. The moon did not just have an internal ocean that froze once in a dramatic cracking episode. It experienced a thermal evolution, a history of warming and cooling driven by forces that changed over time, leaving behind surface features whose ages and characteristics vary from region to region. And this is where the detailed structure of Ithaca Chasma itself becomes a diagnostic tool. The canyon is not a single straight crack. It is a branching system of fractures with specific geometric properties that encode information about the stress field that created them. The main trough of Ithaca Chasma runs in a generally north-south direction, but it does not follow a perfectly straight line. It curves, widens, narrows, and branches as it crosses the surface. The walls are terraced, with the interior stepping down in discrete levels, separated by flat benches, a structure characteristic of a graben, formed by normal faulting in an extensional regime. When a crust is pulled apart, blocks of material drop downward between the separating faults, creating the stepped profile. The width of the graben, the spacing of the terraces, and the depth of the central trough all encode information about the thickness and mechanical properties of the lithosphere at the time of formation. Cassini's imaging also revealed sets of smaller tectonic lineations. Linear features on the surface created by faulting or fracturing in several regions outside the main canyon. These are not branches of Ithaca Chasma. They are independent features with their own orientations and their own histories. In 2020, Ferguson and colleagues mapped small impact craters and tectonic features in high-resolution Cassini images across multiple regions of Tethys. They measured the orientations of the lineations and compared them to the dominant direction of Ithaca Chasma. The results were revealing. Ithaca Chasma has a mean orientation between roughly 15 and 30 degrees from north, but the lineations in the surrounding regions showed significantly different orientations. One region had a mean at 103 degrees, another at 116 degrees, a third at 78 degrees, and a fourth at 161 degrees. None of them aligned with Ithaca Chasma. This meant that the tectonic features outside the canyon were formed by different stress mechanisms than the ones that created the main rift. The moon had experienced multiple distinct episodes of crustal deformation, each driven by its own pattern of stress, each leaving its own set of fractures on the surface. Within Ithaca Chasma itself, the team identified features that ran approximately perpendicular to the canyon's dominant direction, cross-cutting the main structure. These perpendicular fractures implied yet another phase of stress activity, one oriented at right angles to the original extensional forces. The surface of Tethys was not the product of a single dramatic event. It was a palimpsest, a record written over itself in multiple layers, each layer representing a different episode of internal or external stress, separated in time. This complexity matters because it constrains the explanations. A single freeze and crack event in which an internal ocean solidifies and the expanding ice splits the crust along one major line predicts a relatively simple fracture pattern, one dominant rift, perhaps with some minor branching, oriented in a way that reflects the stress geometry of volumetric expansion beneath a spherical shell. Ithaca Chasma partially fits this description, but the additional lineation families do not. They suggest that the stress field on Tethys changed over time, that the forces shaping the surface were not static, but evolving, and that the moon's tectonic history involved multiple chapters rather than a single page. One possible explanation for the variable stress directions is tidal forcing. When a moon orbits a planet on a slightly eccentric path, the changing distance to the planet produces changing tidal forces on the moon's surface. These tidal stresses vary in both magnitude and orientation across the surface, and they vary over the course of each orbit. If Tethys once had a more eccentric orbit than it does today, the cyclic tidal stresses could have produced fractures in multiple orientations across different regions. The fact that Tethys currently has almost zero orbital eccentricity does not rule this out, because the eccentricity may have been significantly higher in the distant past, particularly if the moon was involved in an orbital resonance with another satellite that has since been disrupted. However, Ferguson and colleagues noted that the effectiveness of tidal stresses on Tethys is limited by the moon's very low current eccentricity. The stress field produced by tidal forces on a nearly circular orbit is too weak to generate significant fracturing. If tidal stresses did play a role, they had to have operated during a different orbital configuration that no longer exists, which pushes the question back to what that earlier configuration looked like and why it changed. To understand how planetary scientists piece together a thermal and structural history from surface features alone, It helps to recognize the fundamental distinction between different types of linear features on icy worlds. Not every crack is a canyon, and not every canyon is a graben. On Earth, where we have the luxury of walking across terrain, drilling into rock, and measuring stress directly with instruments, classifying geological features is comparatively straightforward. On a distant icy moon imaged from orbit, everything has to be inferred from shape, shadow, and context. A simple fracture is a break in the surface with no significant displacement. The two sides of the crack sit at roughly the same level. This indicates tension. The crust was pulled apart, but the stress was not sustained or strong enough to cause one side to drop relative to the other. Simple fractures are common on many icy moons and can be caused by tidal stress, thermal contraction, or minor impact-related strains. A graben, by contrast, involves significant vertical displacement. A block of crust drops downward between two parallel or subparallel faults, creating a flat-bottom trough bounded by steep walls. This requires a more substantial extensional force, one that does not merely crack the surface, but physically separates and lowers a section of the lithosphere. Ithaca Chasma is a graben. Its flat floor sections, its terraced walls, and its lateral extent all mark it as a major extensional feature, not a surface scratch. A rift is a broader term describing a zone where the crust is being pulled apart across a wide area, often involving multiple parallel or on-echelon faults, rather than a single clean break. Ithaca Chasma shows rift-like characteristics in places where subsidiary faults fan outward from the main trough, but its dominant expression is a single well-defined graben that can be traced coherently for over 1,000 kilometers. Understanding this classification helps frame what kind of force was needed. A global-scale graben on a body as small as Tethys demands extensional forces operating across a huge fraction of the moon's surface. The crust was being pulled apart from below or from within, and the strain was large enough to produce a trough 100 kilometers wide and several kilometers deep. This is not the signature of a surface stress like thermal contraction or magnetospheric weathering. This is the signature of something happening deep inside the moon, something that physically expanded the interior or reshaped the structure of the ice shell across a significant fraction of the body. The evidence from crater relaxation adds another dimension to this picture. Not all craters on Tethys are equally degraded. Some retain relatively sharp rims and well-defined profiles. Others are softened almost beyond recognition, their rims slumped, their floors raised nearly to the level of the surrounding terrain. The degree of relaxation varies geographically, with some regions showing more degraded craters than others. This spatial variation in relaxation reflects spatial variation in past thermal conditions. Regions where craters are more relaxed experienced higher heat flows, which softened the ice and allowed gravity to reshape the topography more efficiently. The pattern that emerges from mapping this relaxation across the surface is not random. It clusters around regions that show other signs of tectonic or thermal activity, including the area near Ithaca Chasma and the Telemus Basin. The moon's thermal history was not spatially uniform. Certain regions were warmer than others for sustained periods, and the warmest regions correlate with the most tectonically altered terrain. This correlation is exactly what you would expect if the heat source responsible for the canyon and associated fracturing was internal and localized, or at least concentrated in specific zones rather than distributed uniformly throughout the entire interior. The Telemus Basin itself deserves a moment of attention. Named after a figure from Greek mythology, it is a large, degraded impact basin, roughly 270 kilometers in diameter, located in the northern hemisphere of Tethys. Unlike Odysseus, which retains much of its multi-ring structure despite viscous relaxation, Telemus has been so heavily modified by subsequent processes that its original topography is difficult to reconstruct. Its floor has relaxed significantly, and the basin is partially overprinted by Ithaca Chasma related fractures. The high degree of relaxation suggests that the ice in this region was especially warm at some point after the impact, allowing the crater to lose its topographic expression far more rapidly than impacts in cooler regions. The 2023 study of heat flux variations specifically highlighted this basin as a location where thermal conditions were extreme relative to expectations for a moon of Tethys's composition. There is one more set of details from the Cassini era that deepens the puzzle. Cassini's global color mapping and thermal observations of Tethys revealed two distinct surface-scale phenomena that initially seemed unrelated to the tectonic story, but turned out to illustrate just how many processes are superimposed on the same terrain. The first was a dark equatorial band. From a distance, Tethys looks uniformly white, but Cassini's enhanced color maps showed a clearly defined belt of slightly darker material wrapping around the equatorial zone, with brighter polar caps above and below. The band had been faintly visible in Voyager images, but was poorly understood. A team led by Paul Schenk at the Lunar and Planetary Institute solved the puzzle by tracing the pattern to the interaction between Tethys's orbital motion and Saturn's magnetosphere. High-energy electrons trapped in the magnetosphere co-rotate with Saturn, but at Tethys's orbital distance they travel slower than the Moon itself. The result is that these electrons preferentially strike the trailing hemisphere and the equatorial latitudes, chemically darkening and altering the ice. The polar regions, geometrically shielded from this bombardment, remain bright. The dark band is not a geological feature. It is a radiation weathering pattern painted onto the surface by decades of charged particle bombardment. But it matters for the broader story because it demonstrates that Tethys's surface is not just a geological record. It is also a record of the space environment the Moon has inhabited for billions of years. Every process, impact cratering, tectonic fracturing, thermal relaxation, radiation weathering, leaves its own layer of information on the same surface, and separating them is one of the core challenges of reading this moon. The second was a thermal anomaly. Observations using Cassini's composite infrared spectrometer revealed that the daytime surface temperature distribution displayed a shape that researchers compared to an arcade game character. A warmer region surrounded by cooler areas in a configuration that did not follow the simple latitude-dependent temperature gradient you would expect from solar heating alone. The pattern, sometimes informally called the Pac-Man thermal anomaly, was attributed to differences in thermal inertia across the surface. Regions bombarded more heavily by Saturn's magnetospheric electrons develop a compacted or sintered surface layer that absorbs and re-emits heat differently from undisturbed terrain. The thermal anomaly is a surface phenomenon rather than a reflection of deep internal heat, but it underscores how tightly entangled the different processes on this moon really are. Solar illumination, particle bombardment, surface texture, and geological history all contribute to the thermal signature. Disentangling them requires combining imaging data, spectral data, and thermal data simultaneously, and even then ambiguities remain. Taken together, the evidence from Cassini's 13 years of observation paints a portrait of a moon that is far more geologically complex than its featureless white appearance suggests. The surface is not a blank canvas. It is a layered document written in crater densities, fracture orientations, relaxation profiles, radiation weathering bands, and thermal variations, and every layer records a different chapter of the moon's internal and external history. The most important chapter, the one that created Ithaca Chasma, requires a source of heat that Tethys' own composition cannot provide. The moon has almost no rock. It has almost no radioactive fuel. Its current orbit is circular, and its present-day tidal heating is negligible. And yet, the canyon, the relaxed craters, and the elevated heat flux values all testify that the interior was once significantly warmer than it should have been. Something heated this moon from within, and the amount of heating was not trivial. Depending on the model assumptions, the global dissipation rate required to explain Ithaca Chasma's formation ranges from roughly 20 gigawatts to over 100 gigawatts. For context, that is comparable to or even exceeding the estimated tidal heating powering the active plumes of Enceladus today. Where did that energy come from? The answer cannot lie in Tethys alone. A nearly pure ice body this size, with almost no internal radioactive material, cannot generate that kind of heat by itself at any point in its history. The energy has to come from outside, from the gravitational environment, from the orbital dynamics, from the interactions between Tethys and the other bodies in the Saturnian system. And this is where the investigation leaves the surface and enters the realm of orbital mechanics, where the positions and resonances of moons billions of years ago determine whether a small frozen world cracked open or remained whole. The critical insight emerged from models that asked a question researchers had not initially considered central to Tethys' story. What if Tethys and Dione, the next major moon outward, were once locked in an orbital resonance that no longer exists? What if the gravitational interaction between those two moons, amplified by the specific geometry of their orbits, pumped energy into Tethys at rates sufficient to maintain an internal ocean and eventually crack the crust? The mathematics of that scenario and the physical consequences it predicts are the subject of what comes next, and they begin with a mechanism that is already proven to work on another moon in this same system. A moon that is still warm, still active, and still erupting ice into space at this very moment, powered by the same kind of gravitational engine that may have once driven the forces that scarred Tethys on a scale the moon should never have been able to survive. The answer to how Tethys cracked begins not with the moon itself, but with one of the most unusual properties of one of the most common substances in the universe. Water, in solid form, takes up more space than it did as a liquid. This is not normal. The overwhelming majority of materials in nature behave in the opposite way. When most liquids freeze, their molecules pack more tightly together, the material contracts, and the solid form is denser than the liquid. Iron does this. Carbon dioxide does this. Ammonia does this. Water does not. When water molecules transition from a disordered liquid state to the ordered hexagonal lattice of ice, the geometry of the hydrogen bonds forces them into an arrangement that is roughly 9% less dense. than the liquid. The solid floats on the liquid. The frozen form is bigger than the melted form. This single molecular quirk is the reason lakes freeze from the top down instead of the bottom up. It is the reason that ice floats. And it is quite possibly the reason an entire moon cracked open. The freeze expansion hypothesis for Ithaca Chasma's origin rests on this property applied at planetary scale. The idea was first proposed in the early 1980s, shortly after the Voyager flybys revealed the canyon's existence. The logic runs as follows. Early in its history, Tethys possessed an interior that was at least partially liquid. Whether this was a global subsurface ocean or a thick shell of warm, mobile ice depends on assumptions about the moon's thermal state. But the key point is that a significant volume of the interior existed as liquid water or as ice warm enough to deform fluidly rather than behave as a rigid solid. The outer shell, exposed to the cold vacuum of space, froze first. Over time, this frozen shell thickened from the outside inward, growing progressively deeper as the thermal energy from the interior radiated away into space. Eventually, the liquid water beneath was sealed inside a rigid, frozen casing. Then, the interior froze. And as it froze, it expanded. The 9% volume increase that occurs when water transforms to ice is modest at the scale of a glass of water. At the scale of a moon's interior, it becomes an irresistible force. If even a fraction of Tethys's total volume transitioned from liquid to solid while the outer shell was already locked in place, the expanding interior would press outward against the crust with pressures that the ice shell could not withstand. The shell had to give. It had to crack. The predicted result of this process is an extensional fracture, a rift where the surface is pulled apart to accommodate the increased volume of the interior. The fracture's orientation and geometry would depend on the stress distribution within the shell, which in turn depends on the shell's thickness, its mechanical properties, and the rate and uniformity of the internal freezing. For a spherically symmetric freezing event, the stress field would be roughly isotropic, meaning fractures could develop in any orientation. But real moons are not perfect spheres with perfectly uniform shells. Variations in crustal thickness, thermal conductivity, and pre-existing weaknesses from earlier impacts would channel the fracture along a preferred path, producing a single dominant rift rather than a network of randomly oriented cracks. Ithaca Chasma's properties match this prediction in several important ways. Its scale, stretching nearly 3/4 of the moon's circumference, is consistent with the magnitude of extensional strain that global freeze expansion would produce. Its character as a graben, with a block of crust dropped between two parallel faults, indicates an extensional regime where the surface was being pulled apart rather than compressed. And its orientation, running as a roughly coherent structure from north to south, suggests that the stress found a preferred path through the shell, possibly guided by pre-existing variations in crustal thickness, or by the thermal geometry of the freezing front. But freeze expansion alone does not explain everything. The mechanism requires a liquid interior, and maintaining a liquid interior requires heat. This is where the hypothesis, elegant as it is in its mechanics, runs headlong into the composition problem. Tethys has almost no rock. The density tells us that clearly. A body made of nearly pure water ice contains almost none of the radioactive elements that generate sustained internal heat in rocky worlds. The long-lived isotopes of uranium, thorium, and potassium that keep Earth's interior warm for billions of years are concentrated in silicate minerals and Tethys has barely any. Standard thermal evolution models for a body of this composition and size predict that whatever primordial heat Tethys retained from its formation would have dissipated within the first billion years or so. The interior should have frozen solid long before the solar system reached its current age. And yet the heat flux evidence says the interior was warm. The lithospheric thickness inferred from Ithaca Chasma's structure says it was warm. The relaxation of craters across the surface says it was warm. The geological record is unambiguous. Tethys was hotter than its own composition can account for, and it stayed hot for long enough to leave a record that persists 4 billion years later. Something outside the moon was pumping energy into it, and the most compelling candidate for that energy source is the same mechanism that is demonstrably, visibly, and spectacularly operating on another moon in the Saturnian system right now. Enceladus orbits Saturn roughly 238,000 kilometers from the planet's center, closer than Tethys and significantly smaller, with a mean radius of only about 252 kilometers. By every standard metric, Enceladus should be even more geologically dead than Tethys. It is smaller. It has less internal volume to retain heat. It is composed of ice and rock, but the rock fraction is not large enough to provide sufficient radiogenic heating to explain what is happening on its surface. And yet, Enceladus is erupting. The south polar region of the moon is fractured by 4 roughly parallel fissures, known informally as the Tiger Stripes. From these fissures, jets of water vapor and ice particles erupt continuously into space, rising hundreds of kilometers above the surface before falling back or escaping into Saturn's E-ring. The material contains water, salts, silica nanoparticles, and organic molecules. Beneath the ice shell, the moon harbors a global subsurface ocean of liquid water kept warm by ongoing internal heating. Enceladus is, against all intuitive expectation, an active world. What Cassini found in those plumes transformed how scientists think about small, icy bodies. The spacecraft flew directly through the erupting jets on multiple occasions, sampling the material with its instruments and analyzing its composition in detail. The water vapor was expected. The ice grains were expected. What was not expected was the chemistry. The plume material contained sodium and potassium salts at concentrations consistent with water that had been in prolonged contact with the rocky seafloor. It contained tiny grains of silica, specifically nanometer-scale particles of silicon dioxide, that laboratory experiments showed could only form under very specific conditions. Hot water, at least 90 degrees Celsius, interacting with rock in an alkaline environment. That meant the ocean floor of Enceladus was not just wet, it was hydrothermally active. Hot water was circulating through rocky material at the base of the ocean, leaching minerals and creating the chemical conditions that on Earth are associated with deep-sea hydrothermal vents. Cassini also detected molecular hydrogen in the plume, a gas that is produced when water reacts with certain iron-bearing minerals at high temperatures, a process called serpentinization. And in its final years, the spacecraft detected complex organic molecules in the ice grains, compounds with masses exceeding 200 atomic mass units, far larger and more structurally complex than the simple organics found in comets and interstellar space. The ocean of Enceladus was not just liquid. It was chemically rich, thermally active, and producing the kinds of compounds that on Earth are considered building blocks for biology. The energy source driving all of this is tidal heating, powered by Enceladus's orbital resonance with the larger moon, Dione. Enceladus and Dione are currently locked in a 2-to-1 mean motion resonance, meaning Enceladus completes exactly 2 orbits for every 1 orbit Dione completes. This resonance forces a small but persistent eccentricity into Enceladus's orbit, preventing it from settling into a perfect circle. Because the orbit is slightly elliptical, the distance between Enceladus and Saturn changes over the course of each revolution. When the moon is closer to Saturn, the tidal forces are stronger, flexing and stretching the moon's interior. When it is farther away, the forces relax. This rhythmic flexing, repeated every orbit, generates friction within the ice and rock of the interior. Friction produces heat, and that heat, accumulating over millions of years, is sufficient to maintain a liquid ocean beneath the frozen shell and power the eruptions observed at the Tiger Stripes. The mechanism is proven, it is observed, it is measured, and the principle is not unique to Enceladus. Any moon whose orbit is forced into an eccentric shape by a resonance with another body will experience tidal heating. The magnitude of the heating depends on the eccentricity, the size of the moon, its distance from the planet, and the rigidity of its interior. Jupiter's moon, Io, the most volcanically active body in the solar system, is heated by the same basic process, driven by its resonance with Europa and Ganymede. Europa's subsurface ocean, beneath a shell of ice perhaps 10 to 30 kilometers thick, is maintained by the same mechanism. Tidal heating is not speculative. It is one of the primary energy sources shaping the geology of moons throughout the outer solar system. The question for Tethys is whether this mechanism operated there in the past, even though it does not operate there today. Tethys's current orbit is almost perfectly circular. Its eccentricity is effectively 0. In this configuration, there is no significant tidal flexing and no significant tidal heating. The moon is gravitationally quiet, but orbits are not static over the lifetime of a solar system. Moons migrate. They drift inward or outward as they exchange angular momentum with their parent planet through tidal interactions. As they migrate, they pass through configurations where their orbital periods fall into specific ratios with other moons. When those ratios hit exact integer relationships, resonances occur. And resonances, as Enceladus demonstrates, can transform a geologically dead world into an active one. In 2008, Chen and Nimmo proposed that Tethys and Dione were once locked in a 3-to-2 mean motion resonance. In this configuration, Tethys would have completed 3 orbits for every 2 orbits completed by Dione. The resonance would have forced eccentricity into Tethys's orbit, producing tidal flexing and sustained internal heating. The heat would have been sufficient to maintain a subsurface ocean. When the resonance was eventually disrupted, whether by tidal migration moving the moons out of the resonant ratio, by a large impact altering Tethys's orbital parameters, or by some other dynamical event, the eccentricity would have damped quickly. The tidal heating would have ceased, and the ocean would have begun to freeze. The freezing ocean, expanding as it solidified, would have cracked the crust and produced Ithaca Chasma. The elegance of this model is that it explains both the heat source and the fracture mechanism in a single coherent narrative. The resonance provides the energy, the ice expansion provides the crack, and the disruption of the resonance provides the timing trigger, the moment when the heating stops and the freezing begins. In 2019, a study by Hesselbrock and colleagues expanded the resonance analysis significantly. They investigated the orbital phase space of the Tethys-Dione system and identified conditions under which Tethys could be captured into a 2-to-1 mean motion resonance with Dione, a different and potentially even more powerful resonant configuration than the 3-to-2 scenario Chen and Nimmo had considered. In the 2-to-1 resonance, Tethys would complete 2 orbits for every one of Dion's, and the gravitational interaction would pump even more eccentricity into Tethys's orbit. The researchers showed that capture into this resonance is physically plausible if Saturn's dissipation factor, a parameter describing how efficiently the planet's interior converts tidal energy into heat, was lower in the distant past than previously assumed. A lower dissipation factor means faster tidal migration of the moons, which in turn means the moons would have passed through resonant configurations earlier in the system's history and potentially been captured for significant periods. The energy implications were dramatic. Depending on the assumed value of Saturn's dissipation factor at the time of the resonance, the resulting tidal dissipation rate within Tethys ranged between 20 and several hundred gigawatts. For perspective, the current tidal heating of Enceladus is estimated at roughly 5 to 16 gigawatts. A dissipation rate of several hundred gigawatts in Tethys would represent heating far more intense than what Enceladus experiences today. It would have been more than sufficient to maintain a substantial internal ocean and to produce the elevated heat fluxes recorded in the structure of Ithaca Chasma and the relaxation profiles of craters across the surface. The study also examined the fracture orientations predicted by this scenario. As a moon migrates outward from its planet during and after a resonance, the expansion of its orbit produces changes in the moon's rotational and tidal stress field. The resulting surface stresses would generate fractures with specific orientations that depend on the direction and rate of orbital expansion. The researchers compared these predicted orientations to the observed fracture directions in the high latitude portions of Ithaca Chasma and found that they corresponded. The match was not perfect, but it was consistent enough to support the idea that the orbital expansion, associated with the resonance and its aftermath, contribute to the stress pattern that created the canyon. If the resonance scenario is correct, the full sequence of events on Tethys would have unfolded roughly as follows. Early in the solar system's history, Tethys orbited closer to Saturn than it does today. Tidal interactions with the planet caused it to migrate outward. During this migration, its orbit passed through a configuration where the orbital period locked into an integer ratio with Dione's period, either 3-to-2 or 2-to-1. The resonance forced eccentricity into Tethys's orbit. The eccentric orbit produced tidal flexing. The flexing generated internal heat. The heat maintained a liquid water ocean beneath the frozen outer shell, possibly for hundreds of millions of years. Then, the resonance broke. Perhaps the moons migrate far enough that the resonant lock could no longer be sustained. Perhaps a large impact, possibly the one that would later create Odysseus, delivered enough energy to alter Tethys's orbital parameters and knock it out of the resonance. One study noted that a sufficiently large and slow impact, roughly 250 kilometers in impactor diameter at a speed of about half a kilometer per second, could plausibly have disrupted the Tethys-Dione resonance. However the disruption occurred, once the resonance was broken, Tethys's eccentricity rapidly damped towards zero. The tidal heating shut down, and the interior began to cool. What happened next was not instantaneous. The transition from a warm, ocean-bearing moon to a fully frozen, geologically dead world unfolded over a period that may have lasted millions of years. And the dynamics of that transition are central to understanding why Ithaca Chasma looks the way it does. When the tidal heating ceased, the interior did not freeze all at once. The outer shell was already rigid, locked in place at the temperatures prevailing near the surface. The freezing front advanced inward from this shell, millimeter by millimeter, year by year, converting liquid water into solid ice at the boundary between the two phases. Each layer of newly formed ice expanded against the layer above it, adding incrementally to the outward pressure on the shell. In the early stages, the strain was small. The shell could absorb it elastically, stretching slightly without breaking, but the strain accumulated. With every passing century, with every additional kilometer of ocean that crystallized into ice, the total volume mismatch between the expanding interior and the rigid exterior grew larger. At some point, the accumulated stress exceeded the yield strength of the ice shell. The shell failed. A fracture nucleated, probably at a point of pre-existing weakness. An old impact scar, a region of thinner crust, a zone where the local heat flux had been slightly higher and the ice slightly weaker. Once the fracture initiated, it propagated rapidly, extending across the surface as the stress found its path of least resistance through the shell. This initial break would have been the first stage of what became Ithaca Chasma. But the freezing did not stop when the first crack opened. The ocean beneath was still liquid. The freezing front continued to advance. More ice formed. More expansion occurred. The original fracture widened and deepened as additional strain accumulated. New faults formed parallel to the first, creating the terraced walls that Cassini would later image in detail. Each terrace may represent a discrete phase of faulting, a period when enough new strain had built up to trigger the next block of crust to drop between the bounding faults. The terrace structure of Ithaca Chasma is not merely decorative. It is a record of episodic failure, a staircase carved by repeated pulses of expansional stress as the interior froze, layer by layer. Subsidiary fractures branching outward from the main canyon would have formed as the stress field evolved. Once the primary rift opened, it altered the stress distribution in the surrounding shell, concentrating strain at angles to the main fracture and producing secondary breaks that radiate outward. The perpendicular lineations that Ferguson and colleagues mapped may also belong to this phase, recording a time when the stress regime shifted as the geometry of the freezing interior changed and the remaining pockets of liquid migrated or shrank. Eventually, the ocean froze completely. The last liquid water crystallized into ice. The expansion ceased. The stress dropped to zero. And the surface, fractured and deformed by the cumulative effect of the entire freezing process, settled into the configuration it would carry for the next 4 billion years. This reconstruction is compelling, but it carries substantial uncertainties that must be stated plainly. The resonance capture depends on the value of Saturn's dissipation factor, which is not well constrained for the distant past. Recent measurements of the current orbital migration rates of Saturn's moons, derived from astrometric data spanning over a century and refined by Cassini tracking data, have suggested that tidal dissipation within Saturn may be more complex than a single constant value can describe. Some models propose that dissipation varies with time or with the forcing frequency of each moon, a concept known as resonance locking. These models produce different predictions for whether and when specific resonances would have occurred. The question of Saturn's internal tidal response remains an active area of research, with significant implications for the histories of all its moons. The age of Ithaca Chasma itself is model dependent. The estimate of approximately 4 billion years rests on a specific impact chronology model. Alternative chronology models, which use different assumptions about the impactor population in the outer solar system, produce younger estimates, potentially as young as several 100 million years. The relative age ordering. Ithaca Chasma, older than Odysseus, appears robust across different models, but the absolute ages carry uncertainties large enough to affect which resonance scenarios are viable. And there is one more piece of the surface record that does not fit neatly into any existing model. A discovery so unexpected that when the images were first processed, scientists were not sure they were seeing real features at all. In April of 2015, Cassini captured enhanced color images of Tethys' northern hemisphere under illumination conditions that had not been available earlier in the mission. As Saturn's system moved into its northern summer, high northern latitudes became increasingly well lit, and for the first time, large areas of terrain that had previously been in shadow or viewed at unfavorable angles were imaged in multiple spectral filters simultaneously. When the clear, green, infrared, and ultraviolet filter images were combined to highlight subtle color differences invisible to the human eye, something extraordinary appeared on the surface. Thin, curved, reddish streaks arced across the ice. They were narrow, only a few kilometers wide, but they extended for hundreds of kilometers across the terrain. They cut across older features, including impact craters, indicating that whatever created them had operated after the craters formed. Their color was distinctly reddish in the enhanced images, a striking anomaly on a moon whose surface is otherwise among the most color-neutral in the Saturnian system. And their shape was not random. They followed smooth, sweeping curves that resembled the arcs of great circles on the moon's surface. Paul Schenck of the Lunar and Planetary Institute described the discovery by noting how surprising it was to see how extensive the features were. Paul Helfenstein of Cornell University pointed out that the arcs must be geologically young because they cross-cut older terrain, but cautioned that their absolute age in years remained unknown. Several possible explanations were considered. The reddish material could be chemically altered ice, exposed at the surface through fracturing, with impurities that produce the distinctive color. It could be the residue of outgassing from the interior, material released through cracks too narrow to resolve in the available images. Or the arcs could mark the surface expressions of subsurface fractures that have not quite broken through to the topographic surface but have altered the ice above them through thermal or chemical processes. Cassini scientists noted that reddish features are extremely rare on Saturn's moons, with only a few small examples seen on Dione, but are much more common on Jupiter's geologically active moon Europa, where similar coloration is associated with salts and irradiated sulfur compounds linked to the subsurface ocean. The comparison to Europa is provocative but must be handled with care. Tethys shows no current evidence of a subsurface ocean, no active plumes, no measurable heat excess at the surface. Its geological activity, by every available measure, ceased long ago, and yet here on its surface are features that appear young, that display unusual chemistry, and that cut through ancient terrain with a freshness that sits uneasily next to the deep age of everything around them. The red arcs have not been explained. Cassini's mission ended in September of 2017, when the spacecraft was deliberately plunged into Saturn's atmosphere, and no subsequent mission has returned to the Saturnian system. The resolution of the images available is not sufficient to determine whether the arcs correspond to actual fractures in the surface or to some other kind of feature. The chemical composition of the reddish material has not been identified. The arcs remain an open question, a reminder that even after 13 years of dedicated orbital observation, Tethys is still capable of producing surprises that resist easy explanation. What the full body of evidence tells us, from the canyon to the craters to the red arcs, is that Tethys experienced a geological history far richer and more violent than its quiet present-day appearance suggests. The moon was heated, probably by tidal forces during an ancient orbital resonance. It maintained a subsurface ocean, possibly for an extended period. When the heat source was removed, the ocean froze. The freezing expanded the interior and cracked the crust, producing a canyon system that spans nearly 3/4 of the circumference. Subsequent impacts, including the massive Odysseus event, further modified the surface. And at some point, through a mechanism not yet understood, thin reddish streaks were painted across the northern ice. This is not the biography of a dead world. It is the biography of a world that lived intensely, briefly by cosmic standards, and then stopped. The activity ceased. The heat dissipated. The ocean solidified. The eruptions, if there ever were any, went quiet. And the surface froze into a permanent record of everything that had happened. A geological archive locked at temperatures cold enough to preserve every fracture, every crater, and every faint chemical trace exactly as it was left. The meaning of that archive, what it tells us about the nature of small icy worlds and the violence they can endure and preserve, is what this story has been building toward. And it begins with a question that the canyon, for all its enormity, ultimately forces us to confront. What does it mean when a world too small to seem important carries a scar too large to ignore? There is a distinction in geology between worlds that remember and worlds that forget. Earth forgets. Every mountain that rises on this planet is already being torn down by wind, rain, and the slow grinding of glaciers. Every coastline is being reshaped by waves. Every crater that strikes the surface is eroded, buried, subducted beneath tectonic plates, or drowned under sediment within a few 100 million years at most. Earth's surface is alive, restless, and self-erasing. The geological record here is fragmentary, assembled from the scattered ruins of a surface that is always writing over itself. To reconstruct what happened a billion years ago on this planet, scientists must piece together evidence from rare, surviving outcrops of ancient rock, deducing the whole from fragments that amount to a tiny fraction of the original story. Tethys does not forget. It cannot. There is no atmosphere to carry wind. There is no liquid to erode the surface. There is no tectonic system to recycle crust. There is no volcanism to resurface the terrain with fresh material. There is no magnetosphere thick enough to physically alter the shape of surface features. The only processes acting on the surface today are the very slow ones. The steady rain of micrometeorites too small to see. The gradual bombardment of charged particles from Saturn's magnetosphere, and the occasional larger impact that adds a new crater to a surface already saturated with them. These processes modify the texture and chemistry of the topmost layer of ice over millions and billions of years, but they do not erase topographic features. They do not fill in canyons. They do not flatten ridges. They do not smooth away the walls of craters or the scarps of ancient faults. What forms on the surface of Tethys stays there permanently, frozen in place at temperatures where water ice behaves like stone and the passage of time leaves almost no visible mark. This is what makes Tethys so scientifically valuable, and it is what makes Ithaca Chasma so much more than a dramatic visual feature. The canyon is not just a crack in the surface of a small moon, it is a preserved record of a mechanical event, or more precisely, a sequence of events that reshaped the moon's crust on a global scale billions of years ago. Every structural detail of the canyon encodes information about the conditions that existed when it formed. The width of the graben records the magnitude of the extensional strain. The depth records the thickness of the material that failed. The terraced walls record the geometry of the faults that accommodated the displacement. The flexural bulges along the flanks record the elastic thickness of the lithosphere. And the crater density on the canyon floor and walls records, approximately, when the event occurred relative to other features on the surface. Each of these measurements is a sentence in a geological narrative that would have been erased long ago on any world with active surface processes. On Earth, a graben of this age would have been filled with sediment, overprinted by plate tectonics, and eroded beyond recognition within the first few 100 million years. On Tethys, it sits precisely where it formed, 4 billion years later, as legible as the day it opened. This capacity for preservation extends beyond the canyon itself. The relaxed craters scattered across the surface record the thermal conditions that prevailed at different times and in different locations on the moon. The tectonic lineations mapped in multiple orientations record distinct episodes of crustal stress, each driven by different forces, each leaving its own fingerprint in the ice. The mysterious red arcs record a process that no one has yet explained, possibly involving chemistry from the interior, frozen in place before anyone could observe it happening. The Odysseus impact basin records the energy and geometry of a collision that nearly destroyed the moon, preserved in a structure whose rim, floor, and central peak complex have relaxed under viscous flow but not disappeared. Every feature on the surface is a data point from a different moment in the moon's history, and because nothing is erased, the full timeline remains accessible, layered and overlapping, but fundamentally intact. In planetary science, bodies like this are sometimes described as witness plates. In engineering, a witness plate is a piece of material placed in a test environment to passively record the effects of whatever forces act on it. It does not respond. It does not fight back. It simply absorbs the energy and preserves the mark. Tethys has been a witness plate for the solar system for 4.5 billion years. Every impact that struck it, every tidal stress that flexed its crust, every thermal pulse that softened its interior left a record on the surface or in the structure of the ice shell. And because the moon's geological engine shut down billions of years ago, the accumulated evidence has not been disturbed by anything other than the relentless but very slow processes of space weathering and continued cratering. This is what separates Tethys from worlds that are more famous and more photogenic. Enceladus is spectacular. Its active plumes, its tiger stripe fractures, and its confirmed subsurface ocean make it one of the most important targets for astrobiology in the solar system. But Enceladus is still geologically active. Its surface is being continuously resurfaced by plume fallback material. The South Polar region is so young that crater counts are nearly useless for establishing ages. The very activity that makes Enceladus exciting also means it is erasing its own early history. Whatever happened to Enceladus in the first billion years of the solar system is gone, overwritten by the ongoing processes that dominate the surface today. Tethys preserves what Enceladus has lost. The two moons may have experienced similar processes: orbital resonances, tidal heating, internal oceans, expansion fracturing, but Tethys's activity stopped early enough that the evidence of those processes survives intact. In a sense, Tethys is a frozen snapshot of a phase that Enceladus may still be passing through. Studying the Tethyan surface is like reading a completed manuscript, while studying Enceladus is like watching a story still being written. Both are valuable, but the completed manuscript preserves details that the ongoing narrative, by its nature, continuously revises. The broader lesson that Tethys teaches is about the hidden geological potential of small icy bodies. Before the Voyager missions, before Cassini, before close-range imaging revealed what these worlds actually look like, the default assumption was that small moons in the outer solar system were inert. They were too small to retain heat. They were too far from the warmth of their parent stars. They lacked the mass and the composition to drive internal geological processes. They were expected to be featureless ice spheres, pockmarked by impacts and otherwise unchanging since the earliest era of the solar system. That assumption has been demolished by nearly every mission that has visited the outer planets. Io turned out to be the most volcanically active body known to science. Europa turned out to harbour a global ocean beneath its fractured ice shell. Enceladus turned out to be erupting geysers of salt water from its south pole. Ganymede turned out to possess its own intrinsic magnetic field, the only moon in the solar system known to do so. Triton, Neptune's largest moon, turned out to be erupting nitrogen geysers, despite orbiting at a distance from any meaningful heat source that should make such activity impossible. And Tethys, quiet and overlooked, turned out to carry a canyon system that stretches nearly 3/4 of the way around its circumference, evidence of forces that operated on a scale entirely disproportionate to its modest size. The pattern across all of these worlds is the same. Small, icy bodies are not the inert, boring objects they were once assumed to be. They are dynamic, complex, and capable of recording enormous geological events that arise from gravitational interactions, tidal forces, and internal phase transitions that have no equivalent on rocky terrestrial planets. The geological vocabulary developed for Earth, built around concepts like plate tectonics, erosion, and volcanism driven by radiogenic heat, is not sufficient to describe what happens on these worlds. Icy moons operate according to a different set of rules where water ice is the dominant crustal material. Tidal heating replaces radioactive decay as the primary energy source, and the expansion of freezing water replaces the contraction of cooling rock as the dominant driver of crustal stress. Ithaca Chasma is perhaps the clearest single illustration of this principle. On a rocky body, a canyon of comparable proportions relative to the parent body's size would require tectonic forces of a kind that only large, geologically active planets can sustain. Mars has Valles Marineris, a canyon system stretching over 4,000 kilometers, but Mars is a planet with a diameter of nearly 6,800 kilometers. The canyon is enormous, but the planet it sits on is enormous as well. The ratio of feature to body, while impressive, is not fundamentally anomalous. On Tethys, the canyon spans a fraction of the circumference that will be equivalent to a trench stretching from the North Pole to the southern tip of Africa on Earth. The body carrying it is barely 1,000 kilometers across. The disproportion is what makes it scientifically instructive. It demonstrates that the forces available in the outer solar system, tidal heating, orbital resonances, and the expansion of freezing water can produce geological features on small bodies that rival the largest structures on much larger worlds. This raises a broader question about what other icy moons might be carrying similar records. The Saturnian system alone contains dozens of moons that have not been imaged at the resolution necessary to reveal features like those on Tethys. The Uranian system, visited only briefly by Voyager 2 in 1986, contains 5 major moons, several of which showed tantalizing hints of geological complexity in low-resolution flyby images. Miranda, the smallest of Uranus's major moons, is the most striking case. In the handful of images Voyager 2 captured during its brief encounter, Miranda displayed a surface unlike anything else in the solar system. Vast ovoid regions called coronae, bounded by concentric ridges and deep grooves, sat embedded in ancient crater terrain with boundaries so abrupt that it looked as though pieces of different worlds had been stitched together. Verona Rupes, a cliff face on Miranda's surface, is estimated to drop between 5 and 20 kilometers from rim to base, depending on the analysis used, potentially making it the tallest known cliff in the solar system. A wall of ice that dwarfs any comparable feature on Earth. Old, heavily cratered plains abutted young, intensely grooved terrain with no transitional zone between them, as though the moon's geological history had lurched between radically different states. Scientists proposed explanations ranging from catastrophic disruption and reaccretion to intense tidal heating during a past resonance with Umbriel, but the data was too sparse to distinguish between them. Miranda's surface was clearly carrying an enormous story, but the single flyby captured only enough pages to know the story existed, not enough to read it. The Neptunian system has been visited only once, and Triton's surface, despite showing clear evidence of geological activity, was imaged at a resolution that left most questions unanswered. The implication is that the surfaces of icy moons throughout the outer solar system may preserve records of ancient geological events comparable to what Tethys has revealed. Records that are simply waiting for instruments capable of reading them. Every small icy moon that was once involved in an orbital resonance, that once possessed a subsurface ocean, that once experienced tidal heating sufficient to thin its lithosphere and crack its crust, could be carrying its own version of Ithaca Chasma, frozen in place and perfectly preserved for billions of years. The outer solar system may be full of witness plates that no one has yet examined closely enough to read, but the scientific caution that defines responsible interpretation of Tethys's surface must be stated clearly, particularly because the visual power of the canyon invites conclusions that go further than the evidence allows. Ithaca Chasma looks, in photographs, like a wound inflicted by a cataclysmic event. The drama of the feature, its scale, its depth, the way it dominates the visible hemisphere, creates an intuitive impression that something sudden and violent happened. The visual language of destruction is powerful, and it is easy to construct a narrative that matches the emotional weight of the image. The moon cracked open, the surface was torn apart, An internal ocean burst through the crust. These phrasings are vivid. They are not all wrong, but they are not precisely right either. And the gap between vivid description and careful science is where misunderstanding grows. The formation of Ithaca Chasma was almost certainly not an instantaneous event. The extensional fracturing of an ice shell, driven by the gradual freezing of an internal ocean, would have occurred over an extended period, possibly millions of years. The crack did not appear all at once in a single dramatic rupture. It grew, propagated, widened, and deepened as the freezing front advanced, and the expansional strain accumulated. The terraced walls suggest multiple phases of faulting, with blocks dropping in sequence rather than in a single collapse. The subsidiary fractures branching outward suggest that the stress field evolved over time, producing secondary features as the primary rift developed. The process was enormous in its cumulative effect, but it was gradual in its execution, operating on geological timescales that would have been imperceptible to any observer standing on the surface. Similarly, the statement that Tethys was split by a canyon requires careful framing. The moon was not split in the structural sense. It did not break into pieces. It did not separate into fragments that subsequently reaccreted. The crust fractured along one dominant rift zone, producing a graben that accommodated the extensional strain from the expanding interior. The moon remained gravitationally coherent throughout the process. Ithaca Chasma is not evidence of a near-destruction event. It is evidence of a controlled failure, a mechanical response by a rigid shell to forces acting from within, relieving strain through fracture rather than through total disruption. The distinction matters because it tells scientists about the magnitude and rate of the stress. The forces were large enough to crack the crust, but not large enough or fast enough to shatter the body. That constraint limits the range of viable formation models. The relationship between Ithaca Chasma and Odysseus must also be described with precision. Crater counting evidence indicates that the canyon is older than the impact basin. This finding has weakened the hypothesis that the impact caused the canyon, but it has not been universally accepted. The ages derived from crater counts depend on the impact chronology model used, and different models produce different absolute ages. Some researchers have argued that under certain alternative chronology assumptions, the relative ages could be closer than the Giese analysis suggested, potentially leaving some room for a causal connection. The majority view in the scientific community favors the interpretation that Ithaca Chasma predates Odysseus, but the question is not entirely closed. Future missions with better imaging resolution and, ideally, the ability to obtain absolute ages through other methods could resolve this debate definitively. The red arcs discovered in 2015 are perhaps the clearest example of a feature that demands humility in interpretation. Their origin has not been determined. Every proposed explanation, chemical impurities, outgassing residue, subsurface fracture expressions, remain speculative. The arcs are real. They are visible in the data. They are geologically young relative to the surrounding terrain, but their cause is unknown. Stating this honestly is not a failure of science. It is an acknowledgement that observation precedes explanation, and that some features on distant worlds will remain unexplained until instruments more capable than those that discovered them are brought to bear. The honest summary of the scientific picture of Tethys as it stands today is this. The moon once possessed a source of internal heat that its own composition cannot explain. The most likely source of that heat was tidal dissipation driven by an ancient orbital resonance with Dione. The heat maintained a subsurface ocean. When the resonance was disrupted, the heat source was removed, and the ocean began to freeze. The expansion of the freezing water cracked the rigid outer shell, producing Ithaca Chasma. Subsequent impacts, including the Odysseus event, further modified the surface but did not create the canyon. The surface preserves evidence of multiple episodes of tectonic stress in different orientations, suggesting a complex and extended geological history rather than a single catastrophic event. The red arcs remain unexplained, and the thermal and structural record preserved in the surface is consistent with this narrative but does not uniquely confirm it. Alternative models, different resonance configurations, different timing, different mechanisms for delivering the initial heat pulse remain under investigation. Resolving these questions will almost certainly require a return mission to the Saturnian system. Cassini's data, extraordinary as it was, has been mined to the limits of its resolution and coverage. Many of the remaining uncertainties hinge on measurements that Cassini was not designed to make. Precise chemical analysis of surface materials, high-resolution topographic mapping of the canyon walls at meter scale, seismic measurements of the interior structure, and thermal profiling of the subsurface to determine whether any residual warmth persists from the ancient heating episode. Future mission concepts that target the Saturnian moons, whether dedicated to Enceladus or to the broader system, could provide these measurements and transform the current picture from a plausible reconstruction into a confirmed history. Until then, what remains is the image itself, and the image is worth sitting with for a moment. Tethys orbits Saturn at a distance of roughly 295,000 kilometers, tracing a nearly perfect circle through a system of rings and moons that has been gravitationally settled for billions of years. It is one of the brightest objects in the solar system, reflecting more visible light than almost any other solid body. A sphere of clean ice that gleams against the dark background of space like a polished white marble. From any distance greater than a few 100,000 kilometers, it appears featureless, smooth, calm. A small world with no atmosphere, no color, no visible activity of any kind. If you did not know what lay on its surface, you would never stop to look at it twice. But running across that surface, stretching from the northern hemisphere, down through the equator, and deep into the south, is a canyon system that extends nearly 3/4 of the way around the moon, 100 kilometers wide, up to 5 kilometers deep, 2,000 kilometers long. A graben formed by the catastrophic expansion of a freezing interior, carved into the crust of a world barely 1,000 kilometers across. The scar is so large relative to the body carrying it that it reshapes the moon's profile against the sky when viewed at certain angles. It is visible from hundreds of thousands of kilometers away. It dominated the very first close-range photographs ever taken of this world, and it dominates every scientific discussion of the moon to this day. Tethys is not breaking apart. It has not been breaking apart for billions of years. The forces that created Ithaca Chasma are no longer operating. The orbital resonance that heated the interior was disrupted so long ago that no measurable signature of it remains in the current orbital dynamics. The internal ocean froze to completion. The expansion ceased. The crust settled into its fractured configuration and has remained there, unchanged in any significant way, across an interval of time so vast that for most of it, life on Earth had not yet emerged from single-celled organisms. The canyon is not a sign of ongoing danger. It is not a symptom of instability. It is not evidence that the moon is fragile or temporary. It is, instead, something quieter and, in its own way, more profound. It is a scar, a healed wound on a body that experienced something enormous and survived. The violence ended. The heat dissipated. The ocean solidified. The crust stopped moving, and the record of everything that happened was locked into the surface, perfectly preserved at 86 Kelvin, in a place where nothing changes, nothing erodes, and nothing fades. There is something unsettling about that stillness, not because it suggests danger, but because it suggests depth. Tethys carries a history that is wildly out of proportion with its present appearance. Looking at the moon from a distance, you see a bright, calm, unremarkable object drifting through Saturn's system. Looking at its surface, you see evidence of forces that reshaped an entire world. The disconnect between those two views, the quiet exterior and the violent past, is what makes Tethys difficult to forget once you have seen it clearly. It forces a recognition that applies not only to this moon, but to every small body in the outer solar system. The surfaces of these worlds are not blank. They are manuscripts written in a language of craters, fractures, relaxation profiles, and chemical traces. They record events that occurred billions of years ago, events driven by gravitational forces, orbital configurations, and internal phase transitions that have no parallel in daily human experience. These records are waiting to be read. And when they are read carefully, the stories they tell are often enormous, far larger than the bodies that carry them. Tethys is not the largest of Saturn's moons. It is not the most famous. It is not the one most likely to harbor life or to attract the next generation of space missions. But it carries something that very few bodies in the solar system carry with such clarity. The preserved evidence of a transformation so large that it reshaped the entire world, frozen in place at the moment the transformation ended, undisturbed for 4 billion years. The canyon does not threaten. It does not warn. It does not signal that anything is coming. It simply records that something happened long ago to a small world made of ice, orbiting a giant planet in the cold outer reaches of the solar system. Something powerful enough to crack the crust from pole to pole. Something driven by forces that have since fallen silent. Something preserved in a record so complete and so permanent that when spacecraft finally arrived, billions of years later, the evidence was still there, waiting on the surface, as clear and as legible as the day it was written. That is what Tethys is. Not a world defined by what it is doing, but by what was done to it. A quiet, frozen, brilliantly white moon drifting through Saturn's system in a nearly perfect circle, carrying 2 co-orbital companions and reflecting sunlight more brightly than almost anything else in the solar neighborhood. And wrapped around its surface, stretching from hemisphere to hemisphere, carved into the ice to a depth of kilometers, and extending for a distance that nearly encircles the globe, is the record of the day the world cracked open from the inside, and then, having cracked, fell silent forever. The scar remains, the moon endures, and in that silence, in that stillness, in that perfect preservation of an ancient and enormous event on a body far too small to seem capable of producing it, Tethys asks a question that planetary science is still learning how to answer. Not what happened here, though that question is far from fully resolved, but something broader and harder. How many other small, quiet, overlooked worlds in the solar system and beyond are carrying records just as enormous, just as disproportionate, just as patiently waiting to be read? The answer almost certainly is more than anyone expects. And the silence of those worlds, like the silence of Tethys, is not emptiness. It is memory.